Good day, everybody. How are you all doing? Today, we are going to talk about properties of pure substances for thermodynamics, used in thermodynamics. So, here I go. So, properties of pure substances. Simple system. A simple system is one in which the effects of motion, viscosity, fluid shear, capillary, and isotropic stress and external fields are absent. So none of these effects are present. Motion, viscosity, fluid shear. Fluid shear is like one layer of fluid sliding over another layer of fluid. Capillary, when a fluid rises up a capillary tube, and isotropic stress, okay, which varies from space to space inside the fluid. Stress is force per unit area, and external force fields are absent. Homogeneous substance, a substance that has uniform thermodynamic properties throughout, is said to be homogeneous. A pure substance has a homogeneous and invariable chemical composition and may exist in more than one phase. Invariable means it's not going to change. Example, water, three phases of water: solid, liquid, and vapor. Mixture of liquid water and water vapor. Carbon dioxide, nitrogen, mixtures of gases such as air, as long there is no change of phase. The state postulate for a simple pure substance states that the equilibrium state can be determined by specifying any two independent intensive property. Remember, intensive and extensive. Extensive depends on the quantity. Intensive is an inherent property that does not depend on the quantity. So this is a diagram of pressure, volume, and temperature. Okay, PVT, pressure, volume, and temperature, three-dimensional. Okay, so pressure is on the vertical axis, volume you may think on the uh, horizontal axis, temperature is in another dimension. Okay, so pressure is along the z-axis, volume may be along the x-axis, temperature on the y-axis. So volume and temperature are in the same plane, xy plane, whereas pressure is in the three-dimensional field. Three-dimensional field, it is in the z-axis, along the z-axis. So different phases in the different combination of pressure, volume, and temperature, and they're highlighted in the diagram for a particular pure real substance. Real substances that readily change phase from solid to liquid gas, such as water, refrigerant 134A, and ammonia, cannot be treated as ideal gases in general. The pressure volume temperature relation or equation of state for these substances is generally very complicated, and thermodynamic properties are given in table form. The properties of these substances may be illustrated by the functional relationship between pressure, volume, and temperature. And when it is zero, this functional value is zero, it's an equation of state. The above two figures illustrate the function for a substance that contracts on freezing and a substance that expands on freezing. Okay, substance that contracts on freezing and substance that expands on freezing. Constant pressure curves on a temperature volume diagram are shown in figure 311. Okay, so let's see. So Water may exist in the compressed liquid region, a region where saturated liquid water and saturated water vapor are in equilibrium, called the saturation region, and superheated vapor region, the solid or ice region, is not shown. Let's consider the results of heating liquid water from 20 degrees Celsius 1 atmosphere while keeping the pressure constant. Okay, we're just heating it, keeping the pressure constant. We will follow the constant pressure process in figure 311. Okay, first place the liquid in a piston cylinder device where a fixed weight is placed on the piston to keep the pressure of water constant at all times. As the liquid water is heated, the pressure is held constant. The following events occur. Process 1 through 2. 1-2 is the temperature and specific volume will increase from the compressed liquid or subcooled liquid state 1 to the saturated liquid state 2. In the compressed liquid region, the properties of the liquid are approximately equal to properties of the saturated liquid state at the temperature. Okay. At state 2, the liquid has reached the temperature at which it begins to boil, called the saturation temperature, and is said to exist as a saturated liquid. Properties at the saturated liquid state are noted by the subscript F and V2 equal to V1. During the phase change, both the temperature and pressure remain constant. According to International Temperature Scale of 1990, ITS 90 water boils at 99.975 degrees Celsius, which for all practical purposes is 100 degrees Celsius when the pressure is 1 atmosphere or 101.325 kPa kilopascal. At state 3, the liquid and vapor phase are in equilibrium, and any point on the line states between states 2 and 3 has the same temperature and pressure. At state 4, the vapor exists and vaporization is complete. The subscript G will always denote a saturated vapor state. Note V4 is equal to Vg. Thermodynamic properties at the saturated liquid state and the saturated vapor state are given in table A4 as the saturated temperature table and table A5 as the saturated pressure table. These tables contain the same information. In table A4, the saturation table is the saturation temperature is the independent property, and in table A5, the saturation pressure is the independent property. The saturation pressure is the pressure at which the phase changes will only occur for a given temperature. In the saturation region, the temperature and pressure are dependent properties. If one is known, the other is automatically known. If the constant pressure heating is continued, the temperature will begin to increase above the saturation temperature 100 degrees Celsius in this example, and the volume also increases. State 5 is called the superheated state because T5, that is temperature in fifth state, is greater than the saturation temperature for the pressure in the vapor is not about to condense. Is not about to condense. Thermodynamic properties for water in the superheated region are found in superheated steam table, table 8-6. This constant pressure heating process is illustrated in the following figure. So here you go. Okay. 1 to 2 compressed liquid, 2 to 3 saturated mixture, and 2 to 3, 3 to 4. From 4 onwards, it is superheated vapor. Here, the whole state of water is shown in a temperature versus volume, specific volume diagrams. Note the small v. Consider repeating this process for under other constant pressure lines as shown below. So notice in each of these lines, there's a different pressure. We initially start at the bottom line at 0.01 megapascal, capital M means megapascal, 10 to the power of 6. Okay. And then you have zero point 0.1. So first one is 0.01 megapascal. One above it is 0.1. Next one above is 1. The fourth line is 8 megapascal. The fifth line is 15 megapascal. The sixth line is 22.09 megapascal. And the last line pressure is 25 megapascal. Notice the critical point. Okay. And critical point in for the case where the pressure is 22.09 megapascal. Uh, temperature on the vertical axis is 373.95, and on the horizontal axis, which is specific volume, that's volume per unit mass, is 0.005155 meter cubed per kilogram. If all of the saturated states are connected, the saturated liquid line is established. If all of the saturated vapor states are connected, the saturated vapor line is established. Okay, one is saturated liquid line, another is saturated vapor line. These two lines intersect at the critical point and, and from what is often called the steam dome. The region between the saturated liquid line and the saturated vapor line is called by these terms: saturated liquid vapor region, wet region, that is a mixture of saturated liquid and saturated vapor, two-phase region, and just the saturation region. Notice that the trend of the temperature following a constant pressure line is increasing, is to increase with increasing volume, and the trend of pressure line following a constant temperature line is to decrease with increasing volume. So here you go. Here you see the dome. On the left, you have the saturated liquid line. On the right, you have the saturated vapor line. In between the dome, you have the saturated liquid vapor region. Okay. On the left of the saturated liquid line, you have the compressed liquid region. On the right of the saturated vapor line, you have the saturated vapor region. Okay. And those different lines show you the effect of temperature. Okay. Okay. PV diagrams for substances that contract on freezing and those that expand on freezing is given in figure 3.21 and 3.22. At temperatures and pressures above the critical point, the phase transition from liquid to vapor is no longer discrete. Okay, so they indicate the critical point. Triple point of water is 0.01 degrees Celsius, see table 3.3. Okay, the critical point of the triple point of water is 0.01 Celsius, triple point. Okay. And the critical point of water is 373.95 degrees Celsius. Okay. So there are different lines. One is for melting. One is for substance that expand on freezing. That is the first dashed line. The solid line going up is the substances that contract on freezing. Okay. And you have vaporization line and saturation line. Okay. On the left of the melting line, you have solid. On the right, you have liquid. Mhm. Process A to B, liquid to vapor transition. Okay. Process C to D, solid to liquid transition, and process E to F, solid to vapor transition. In addition to temperature, pressure, and volume data, tables A4 through A8 contain data for specific internal energy, the specific enthalpy, and the specific entropy. The enthalpy is a convenient grouping of the internal energy, pressure, and volume, and is given by H is equal to U is the internal energy plus BP. PV. H by itself is enthalpy. And enthalpy per unit mass divided by m mass on all both sides of the equation, you get small h is equal to small u plus capital P remains constant but small v. We will find the enthalpy H is quite useful in calculating the energy of mass streams flowing into and out of controlled volumes. The enthalpy is also useful in energy balance during a constant pressure process for a substance contained in a closed piston cylinder device. The enthalpy has the units of energy per kilogram or per unit mass, kilojoule per kilogram. The entropy S is the property defined by the second law of thermodynamics and is related to heat transfer to a system divided by system temperature. Thus, entropy has units of energy divided by temperature. So, since temperature and pressure are dependent on properties using the phase change, two tables are given for the saturation region. Table A4 has the temperature as the independent property. Table A5 has pressure as the independent property. These two uh, tables contain the same information and often only one table is given. Okay, for the complete table A4, the last entry is critical point at 373.95 degrees Celsius. And here is the table. Saturation pressure is the pressure at which the liquid and vapor phases are in equilibrium at a given temperature. Saturation temperature is the temperature at which liquid and vapor phases are in equilibrium at a given pressure. The subscript F, sub F and G, Fg together used in table A4 and A5 refer to the difference between the saturated vapor value and the saturated liquid value region. That is, Ug or UFG is equal to UG minus UF. Similarly, HFG is HG minus HF and SFG is SG minus SF. The quantity HFG is called the enthalpy of vaporization or latent heat of vaporization. It represents the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. It decreases as the temperature or pressure increases and becomes zero at the critical point. Now let's review the constant pressure heat addition process for water shown in figure 311. Since state 3 is a mixture of saturated liquid and saturated vapor, how do we locate it on TV diagram? To establish the location of state 3 is a new parameter called X, called the quality X as defined by X is mass of saturated vapor divided by total mass, or mg divided by mf plus mg. The quality is 0 for saturated liquid and 1 for saturated vapor. So X, the quality, is between 0 and 1. The average specific volume at any state 3 is given in terms of quality as follows. Consider a mixture of saturated liquid and saturated vapor. The liquid has a mass mf and occupies a volume vf. The vapor has a mass mg and occupies a volume vg. So m is equal to mf plus mg, v is equal to mv, and vf is equal to mf vf, vg is equal to mg vg. These are capital V's on the left hand side. So mv is equal to mvf plus mg vg. So you divide by mass all through, you get definition of x is mg by mf is equal to mg divided by actually mg divided by mf plus ms. mf by ms is m minus mg divided by m is 1 minus mx. Note the quantity 1 minus x is often given the name moisture. The specific volume of a standard mixture becomes volume is equal to 1 minus x amount of moisture times Bf plus x Vg. Noted the value of any extensive property per unit mass in the saturation region is calculated from an equation having a form similar to that of the above equation. Let capital Y be an extensive property and let Y be the small y be the corresponding intensive property. Y capital Y over M. Then small y is capital Y over M is equal to small yf plus x times Vg minus or Yg minus Ym f. Okay. Which is same as Yf plus x times Yg. Okay. So what is Yg is or YFE is defined as the quantity inside the parenthesis, which is Yg minus Yf. The term YFG is the difference between saturated vapor and the saturated liquid values of the property Y. Small y may be replaced by any of the values V, U, and S. That means, for example, you can write HFG is equal to Hg minus Hf. So HFG is the property, value of the property difference between the gaseous phase and the fluid phase. It is the value inside the dome, steam dome. Remember, we saw it before. We often use the above equation to determine the quality of a saturated liquid vapor state. The following application is called the lever rule. The lever rule is illustrated below. Okay. So X is amount of gas is A B width of the line AB divided by AC. X is the moisture, right? X is the moisture. So it is AB width of the line AB divided by AC, width of the line AC. A substance is said to be superheated if the given temperature is greater than the saturation temperature for the given pressure. State 5 in figure 311 is a superheated state. In the superheated water table A6, temperature and pressure are the independent properties. The value of the temperature to the right of the pressure is the saturation temperature of the pressure. For the pressure, the first entry in this table is the saturated vapor state at the pressure. Superheated water table, a substance is said to be superheated if given temperature is greater than the saturation temperature for the given pressure. State 5 in figure 311 is a superheated state. In the superheated water table A through 6, T and P are independent properties. The value of temperature to the right of the pressure is set the saturation temperature for the pressure. The first entry in the table is the saturated vapor state at the pressure. And here is the table. Superheated water. Compressed liquid water table, a substance is said to be a compressed liquid when the pressure is greater than the saturation pressure for the temperature. It is now noted that state 1 in figure 311 is called a compressed liquid state because the saturation pressure for the temperature T1 is less than P1. Data for water compressed liquid state are found in the compressed liquid tables A through 7. Table A7 is arranged like table A6 except that the saturation state is a saturated liquid state. Note that the data in table A7 begins at 5 megapascal or 50 times the atmospheric pressure. At pressures below 5 megapascal for water, the data are approximately equal to the saturated liquid temperature at the given temperature. We approximate intensity parameter Y, V, that is VU and H, VU, H and S data as Y is equal to Y fluid at temperature T. The enthalpy is more sensitive to the variation in pressure Therefore, at high pressure, the enthalpy can be approximated by H is almost equal to, that sign is almost equal to HF at temperature T plus VF multiplied by P minus P saturation. For our work, the compressed liquid enthalpy may be approximated by H is almost equal to HF at temperature T. When temperature of a substance is below the triple point temperature, the saturated solid and liquid phases exist in equilibrium. Here we define the quality, the ratio of the mass, that is vapor to the total mass of solid and vapor in the saturated solid vapor mixture. The process changing directly from solid phase to the vapor phase is called sublimation. No liquid in between, just directly going from solid to vapor phase. Data for the saturated ice and water vapor are given in table A8. In table A8, the term SUBL, subl, refers to the difference between the saturated vapor pressure and the saturated solid value. Okay, so YG is FG is YG minus YF. So capital Y is equal to YF plus XH times YFG, where the quality of X of a saturated ice vapor state is given by X is equal to mg divided by mf plus fg. The correct table to use to find the thermodynamic properties of a real substance can always be determined by comparing the known state of the properties in the saturation region. Given the temperature or pressure and one other property from the group V, U, H, and S, the following procedure is used. For example, if pressure and specific volume, that is V, are specified, three questions are asked for the given pressure. Okay. Is V less than Vf? Is Vf less than V less than Vg? That is V between Vf and Vg? Or is Vg less than V? The answer to one of these questions must be yes. If answer to the first question is yes, the state is in the compressed liquid region, and the compressed liquid tables are used to find the properties of the state. If the answer to the second question is yes, that is V is between, specific volume is between V of F and V of G. Okay, so the answer is yes. The state is in the saturated region, and either the saturation temperature table or the saturation pressure table is used to find the properties. Then the quantity is calculated and is used to calculate the other properties U, H, and S. If the answer to the third question, that is the specific volume greater than V of G, okay? If the answer to the third question is yes, the state is in the superheated region, and the superheated tables are used to find the properties. Some tables may not always give the internal energy. When it is not listed, the internal energy is calculated from the definition of enthalpy as U is equal to H minus pressure times specific volume. Find the internal energy of water at given states for 7 megapascal and plot the states on TV, PV, and PT diagram. Okay. So basically you read off the chart. Okay. Temperature versus volume looks like this. Okay. This is pressure versus volume, sorry. Pressure versus volume. This is showing you the triple point. Okay, here they're calculating the internal energy. Okay, they located the given the temperature pressure. Okay, the given you can find out UG. Okay, pressure is 7 pascal, and you can find the saturated liquid property UF. Okay, look at the state 2 on TV, PV, and PT diagrams. Moisture is 5%, from which you can calculate, I mean, Y is 0.05. And then you can calculate the if y is 0.05, then x is 0.95. That's how you get that. Substitute the value of x in this equation. Okay. We could have also used this equation if we wanted. And then you calculate internal energy. Okay. Again, you calculate y, you calculate internal energy. Okay. So here is another problem. Pressure is given, temperature is given. Using table A4 at T is equal to 100 degrees Celsius. P at saturation pressure is only 0.10142 MPa. Since capital P 7 megapascal is greater than the saturation pressure, the state is compressed liquid. Approximate solution U is almost equal to UF at T is equal to 100 degrees Celsius, which is 419.06 kilojoule per kg. Okay. Or we can do the linear interpolation to get the value at 100 degrees Celsius. So once we know the U value, we can do linear interpolation. So we know pressure is 5 at 5 megapascal pressure. U internal energy, specific internal energy is 417.65 at megapascal 10. U is 416.23. Now our pressure is 7, somewhere halfway between 5 and 10. So we can do interpolation, linear interpolation. Okay, and U works out to 417.08. Another problem, pressure is 7 megapascal, temperature is 460 degrees Celsius. Since 460 degrees Celsius is greater than the saturation temperature at pressure is 7 megapascal, the state is superheated. Again, we do linear interpolation to find out U. Okay. Once we know U, then we can look at the state on TV, PV, and PT diagrams. Example 3.2, determine the enthalpy of 1.5 kilogram of water contained in a volume of 1.2 meter cubed at 200 kPa. Recall, we need two independent intensive properties to specify the state of a simple matter. Pressure P is one intensive property and specific volume is another. Therefore, we calculate the specific volume, which is volume divided by mass. Okay. So volume is 1.2 meter cube divided by mass is 1.5 is 1.8 meter cube per kilogram. Pressure, so using table A5, pressure is given as 200 kPa already to us. So from that table, we answered this question, is V less than Vf? No. Is specific volume between Vf and Vg? Yes. If Vg less than V? No. Locate this state on a TV diagram. Okay, we see that the state in two phase of saturation region. So we must find the quality X first. Okay. Once we find the quality, then we find H, okay, which is HF plus X times HFG. And this is another example, internal energy of a refrigerant, temperature 0 and quality is 60 degrees Celsius. Again, we use a table, temperature 0 degrees Celsius, UF is thus 51.63 kilojoule per kilogram, UG is 230.16 kilojoule per kilogram, from which we can calculate. And then this example, consider the closed rigid container of water shown below. The pressure is 700 kilopascal. And the mass of the saturated liquid is 1.78 kilogram and the mass of saturated vapor is 0.22 kilogram. Heat is added to water until the pressure increases to 8 megapascal. Find the final temperature, pressure, enthalpy and internal energy of water. Does the liquid level rise or fall? Plot this process on a PV diagram with respect to saturation lines and critical point. Okay. System is a closed system composed of water enclosed in the tank, property relations, steam tables, process volume is constant, rigid container. For the closed system, the total mass is constant, and since the pressure is 1, in which the volume is constant, the average specific volume of the saturated mixture during the process is small v is capital V divided by m constant, or V2 is equal to V1. Now find V1. Recall that in the two-phase regions at state 1, okay, so we find V1 pressure at 700 kilopascal, okay. State 2 is specified by pressure 2 is 8 megapascal, V2 is also known. So 8 megapascal, Vf is this, Vg is this. So we find answer the question. Is V2 less than Vf? No. Is V2 in between Vf and Vg? No. Then is Vg less than V2? Yes. Okay, interpreting in the superheated tables at 8 megapascal, V is equal to 0.031 meter cube per kilogram, gives this temperature in T2, H2, and U2. Since state 2 is superheated, the liquid level falls. Okay. The relationship among state variables, temperature, pressure, and specific volume is called the equation of state. We now consider equation of state for a vapor or gaseous phase of simple compressible substance. Function of pressure, temperature, and specific volume is 0. For ideal gas, pressure is RT divided by V, where R is the gas constant and takes on a different value for each uh, gas. If a gas obeys this relation, it is called an ideal gas. P times small v is equal to capital R times T. Okay. So R is R0 by R by capital M. The mass is related to the moles n of a substance through the molecular weight or molar mass. See table A1. Okay. So here the mass of air, molar mass of air is 28.97 gram per gram mole, kilogram per kilomole, or pound mass per pound mole. Since 1 kilomole is 1000 gram mole or 1000 gram mole, and 1 kilogram is equal to 1000 gram, 1 kilomole of air has a mass of 28.97 kilogram or 28.970. So small m is n. N is number of moles times molar mass. Okay, molar mass is weight of one mole. Okay, the ideal gas equation is PV equal to RT, V specific volume. So it's capital V divided by M, or you can write PV is equal to MRT. Okay, or you can write PV, P with a V bar is equal to RUT. Okay, RU is 8.3. Okay, P is absolute pressure in megapascal or kilopascal. V is the molar specific volume. It's a molar specific volume. Why? Because capital V is divided by N. N is the total number of moles. So capital V divided by N is the molar specific volume indicated by the symbol V bar. Some of the values of universal gas constant are given here, and here they're doing a problem. Capital R is RU by M. So we know the RU, we know the molar weight, and we can calculate R of air. We can do the calculate R of hydrogen, which is a gas constant per molar mass. Compressibility factor is given by this equation. P of V bar is equal to Z times RU times T. Z is the compressibility factor. It is P times specific volume, molar volume, divided by R times C is the universal gas constant per molar mass times temperature. For an ideal gas, Z is equal to 1, and the deviation of Z from unity measures the deviation of the actual PVT relation for the ideal gas equation of state. The compressibility factor is expressed as a function of the reduced pressure and reduced temperature. The Z factor is approximately same for all gases at the same reduced temperature and pressure, which are defined as T reduced is equal to actual temperature divided by critical temperature. Similarly, P reduced is equal to P divided by P critical, where PCR and TCR are the critical pressure and critical temperature, respectively. The critical constant data for various substances are given in table A1. This is known as the principle of corresponding states. Figure 3.51 gives comparison of Z factors for various gases and supports the principle of corresponding states. So here, okay, with either P or T, okay, so you have the compressibility factor as a function of P or reduced pressure. When either P or T is known, Z can be determined from compressibility chart. This is a compressibility chart with the help of the pseudo-reduced specific volume defined as VR is V actual divided by R times T critical divided by P critical. Figure A15 represents a generalized compressibility chart based on data for a large number of gases. So all these lines are at different temperatures, okay? Different temperatures. If PR less than 10 and TR less than greater than 2 and P less or P less than 10 PCR and T greater than 2 TCR 2. Okay, so they behave as an, I believe, ideal gas. When PR is small, we must take into account that the state is not compressed liquid region on for the given temperature. A compressed liquid state is certainly not an ideal gas state. For instance, the critical pressure and temperature for oxygen are 5.08 megapascal and 154.8 Kelvin respectively. For temperature greater than 300 Kelvin and pressures less than 50 megapascal, 1 atmosphere pressure is only zero point 0.1 megapascal. Oxygen is considered to be an ideal gas. Calculate the specific volume of nitrogen at 300 K and 8 megapascal and compare the result with the value of nitrogen table as specific volume given as. So they go through the calculation and get the value very close to the uh, nitrogen table, which shows that nitrogen is an ideal gas at this state. If system pressure is low enough and the temperature is high enough, P and T are compared to critical values, gases will behave as ideal gas. So consider the TB diagram for water. The figure below shows the percentage of error for the volume. Okay, it's the absolute value of V table minus V idle divided by V table times 100 for assuming water to be an ideal gas. We see that the region for which water behaves as an ideal gas, okay, is the superheated region and depends on both temperature and pressure. We must be cautioned that in this course, when water is the working fluid, the ideal gas assumption may not be used to solve problems. We must use the real gas relation, that is the property tables. Okay. By writing the ideal gas equation twice for a fixed mass and simplifying the properties of an ideal gas at two different states are related by M1 equal to M2. The gas constant is, fill the blanks, so P1 B1 divided by T1 is equal to P2 V2 divided by T2. Okay, so another example, more work. Okay. Many attempts have been made to keep the simplicity of the ideal gas equation of state, but yet account for the intermolecular forces and volume occupied by the particles. Three of these are van der Waals equation, okay, equation of state, P plus A divided by V square multiplied by V minus V. V is the specific volume is equal to RT. A and B are constant given by this equation. Okay, there is another one, and there is the last one. Okay, and here they do a comparison between ideal gas case and the real if we do the correction factors. Notice the result for the Beryl-Bridgman equation compare well with the actual nitrogen data provided by EES in the gaseous or superheated region. That's on the extreme right top. Okay. However, neither the BB equation nor the ideal gas equation provides adequate results in the two-phase region, which is inside the dome, where the gas, ideal or otherwise, assumption false. That's it for today. I will stop here today. If you have any question or comment, write me a note. I'll definitely answer your question. If you have any suggestion, please go ahead and write it in a comment. I will answer to your comment. If you like this video, please give me thumbs up. If you like this video, share with your friends, you and your friends. Please subscribe to my channel by hitting the red subscribe button at the bottom right corner. And please remember, I'll be back tomorrow with something more interesting. Thanks for watching. Take care and be a part of my growing subscriber base by subscribing and let YouTube know that you would like to be notified every time I upload a new video. Again, thanks to my faithful subscribers, and I'll be back again tomorrow with something more interesting, as I said before. Thanks. Bye. Take care. See you later.